In this mini lecture, we will try to explain how to calculate the critical Mach number by using the graphical method. So let's see what is the so-called graphical method in here. We've seen this kind of plot earlier when we introduced the critical Mach number, and we know when the free stream Mach number is 0.61, there's single point A has a sonic speed over the airfoil, which is Mach 1.0. Okay, and also through the discussion for the airfoil across the transonic Mach number regime, and we know how to determine the critical Mach number. So we just look into the detailed flow field over the airfoil surface and find the if there is only one single point has or very small region has sonic Mach number, then we determine that is a critical Mach number. So we estimated the critical Mach number through CFD simulation. And today we will learn to estimate the critical Mach number through another way, which is a graphical method. So we use this slide as an introduction. Okay, so I'm copying that particular condition here, which corresponds to the critical Mach number for this airfoil. Okay, so now let's consider a random point over the airfoil. And then we have if we use a isentropic relation, we'll have this pressure ratio. The P is a local pressure over the a random point of the airfoil, and the P0 is the total pressure in this flow. And then the P over P0 has a relation with a Mach number. Has a relation with a Mach number. So this M is a local Mach number over that random point. Okay, so we will be interested in the pressure coefficient for that random point. Then we have the definition of the pressure coefficient, P minus P infinity divided by half rho U infinity square. Okay, so let's move further, and we know the denominator half rho V square and actually equals half gamma P infinity M infinity square. And we've done this derivation, so we've demonstrated the equivalency for these two denominators. Okay, and then we just take the common terms out, and we can reorganize it. So finally, it can be in the bracket, it can be two ratios. On top is the local pressure ratio with respect to the total pressure, and the denominator is free stream pressure divided by the total pressure. Okay, so we can by replacing the two pressure ratios by using the isentropic relation. So although it looks big, but I think it's quite neat. Yeah. Now we just reorganize it because the exponent has a minus sign, and then we just take off the minus sign, so the terms in the bracket is inversed. Okay. And now let's consider point A. And we know at point A, in this case, for this airfoil at this particular Mach number, or at the critical Mach number, we know the Mach number at point A is 1.0. So if now we replace the m square in the denominator by 1, then we know if the point A reaches sonic, then the pressure ratio is kind of this relation, highlighted relation. So this is a very important relation, and at this free stream Mach number, then it's a critical Mach number. Okay, so let's say how can we use this CP critical to estimate the critical Mach number. Okay, so I'm copying the relation here and also this figure. And so now you can see if the above relation is the CP critical versus the free stream Mach number or the critical Mach number. So if the free stream Mach number changes, increases, and we will also see that actually the CP critical increases, and the relation is plotted in here. Just once you pay attention to the CP critical axis, and you should notice it's inversed. Okay, why is inversed? Because when we deal with the pressure coefficient for the airfoil, it's normally inversed, especially when you plot the pressure coefficient distribution for the upper and the lower surface. Is it inversed? Right, we just follow that type of method, or it's just a kind of a commonly adopted custom. Okay, so now we can use the graphical method to estimate the critical Mach number for a specific case. And just to let you know, the above relation CPCR is general. It applies for any airfoil. Okay, so let's see. Step 1, measure the airfoil at different Mach numbers and find the CP minimum at each airfoil at each Mach number. So for example, we start measuring at 0.4, and then we can find a minimum pressure over the for example, the upper surface. Why minimum pressure? Because if the pressure at that point is minimum, which means it has the highest Mach number, right? So assume now we've done several measurements and we got the minimum pressure or minimum pressure coefficient at each flow condition. So now we have 1, 2, 3, 4, 5, 6 points. Okay, so that's our measurement. And then we move to step 2. What we do is connect the measurement points and generate a Mach CP minimum curve. So we can generate such a curve. And now maybe you already know what happens. How do we get the critical Mach number? So step 3, the critical Mach number corresponds to the Mach number at the cross point, right? So the cross point determines the critical Mach number. Now you can see this is purely a graphical method. The critical Mach number is derived through the cross points, right? So this is, I would say, the magical part. And the only thing is you need to do several measurements. And I would say you need to, although I'm just showing 6 points in here, but in reality you need to do more to have a smoother connection of the red dots. And it will give you a more precise critical Mach number plot, or a more precise critical Mach number estimation. Now you may have a question. Is there a way to do fewer number of experiments to get the critical Mach number? So which means if we want to get the critical Mach number, we don't need to do so many measurements, and it's very expensive to do such high-speed measurements. So that's the idea. Okay, and so this is introduction of the critical method. I believe you can understand now and how to use a graphical method to estimate the critical Mach number. So this is only the first version of the graphical method, but later on in the next 2 classes, we will revisit this graphical method and see to answer the highlighted question here. Okay.